During his time at Cambridge University, Newton made an interesting observation about light. He noticed that when sunlight had passed through his office window, as it went through a prism, the white light had broken up into the constituent colors that we now know make up white light. So basically, as it passed through a prism, it formed sort of a rainbow. And then this band of colors, this is what this is what he had called a spectrum. So Newton had noticed that this spectrum always appeared in a specific order, and the way that we are going to order it to remember it, we're going to order it from lowest to highest frequency, or as you'll see later, that's also the same as from lowest to highest energy. Or we know that frequency and wavelength are inverted or have an inverse relationship, so we could also say they're ordered from highest to lowest wavelength. So the order that Newton had noticed was red, orange, yellow, green, blue, indigo, and violet. Now, to remember this, you've probably learned that trick in like elementary. You learn to remember the name of a person named Roy G. Biv. So this is our mnemonic to remember the order of the colors, again, going from lowest to highest frequency. Now, when we talk a lot about colors, usually indigo kind of goes bye-bye, and the reason for that is we have a really hard time, our eyes, distinguishing the hues of blue and violet. So while indigo is still a proper color that makes up white light, we have a really hard time distinguishing it from blue and violet, so we generally just don't include it in our list, but it is still a proper color. So this whole idea of taking white light and splitting it into its constituent colors, this is what we refer to as dispersion of light. And probably a great famous example of this, for those of you that listen to some good old rock and roll, rock music, we're talking about the great Pink Floyd. So from their album cover, Dark Side of the Moon, you can see we have white light goes in, and the colored spectrum comes out. Credit to Pink Floyd, they also got the order correct and they got the correct refraction. So good on them. We can say that Pink Floyd really loves physics and they understand it. Now, if we take white light and split it up into the colors, can we do the reverse? Yes, all we have to do is take those colors, that rainbow, pass it through another prism, and they will recombine into white light. So this process of taking the 7 colors and putting it back into white light, this is what we refer to as recombination. So when we're talking about dispersion of light, there's a couple of important points. And this is one of the things I was just kind of saying Pink Floyd got right with their album cover. So what we've noted is that shorter wavelengths of light, like violet for example, the shorter wavelengths tend to be the most refractive, whereas our longer wavelengths, they tend to be the least refractive. So when we say the most refractive, we're going to say bends more. And when we say least refractive, we're just going to say it bends less. So we kind of look again, we have our white light coming into the prism, it's starting to disperse. And then we'll see red, it kind of bent a little bit, and then as we go down the spectrum here, we're going to see more and more bending, with violet light having the most bending or the most refraction. This is an important point to know. This gets asked on the diploma quite a bit. A bit later when we look at diffraction, I'll tell you about a mnemonic or a trick I learned from another friend who she had a great way of remembering the difference between refraction and diffraction, but I'll get back to that later. And if you want to have at least a mathematical reason for this, we can look at kind of the index of refraction. So we know that n equals c over v, or instead of v, we could replace that with f lambda, our equation for the universal wave equation. So as the wavelength goes up, so as we start to go from violets all the way up to reds, our index of refraction is going to decrease. This means we're going to have a decrease in bending. Conversely, if we start to decrease our wavelengths, like we start to move towards the violet, as this piece gets smaller, n is going to go up. Because we can kind of see that the index of refraction, it's inversely proportional to the wavelength. So if the wavelength goes up, n goes down, so higher wavelengths, less bending. If lambda goes down, n goes up, so lower wavelengths, more bending. But like I said, this is I'll show you a little bit more about this later when we talk about diffraction. So this is a table just kind of showing the rough boundaries for the colors of the visible spectrum, but this is a very rough table. The boundaries are not exact, especially those of you who are very artistically inclined. You know colors blend and they kind of transition from one to the other, so we don't have any really hard, fast cutoffs. The best thing I could say for you is that as long as you remember that violet light, if you can remember that it's around 400 nanometers or starts there, and kind of red maybe terminates around the 700 nanometer mark, even though I have it as 750 in the table here. As long as you can remember visible lights between 400 nanometers and 700 nanometers, you'll be fine on the assessments, as long as you can remember that key point. We're not going to start to say, okay, at 500 nanometers, do you have blue or green light? Like, that's not really fair. And believe me, the diploma, they won't make these questions very hard. They do have a little bit of, like, empathy for you.